All right, hello. I'm going to go through the activity template that I have as part of my ETP that you are welcome to make copies of, share with your students, whatever you think is appropriate. My school is a Google school, and so we use Google Classroom, which makes it really easy to distribute copies of a spreadsheet to students. So that's why I like to use all the Google Docs all the time. But if you don't have Google Classroom, I know there are some other applications like Doctopus and things that can distribute or whatever system you have. So when you open up the template, you will see this page right here that has a blank chart and an empty data table, as well as some just general instructions and reminders for the students. And notice that there are two tabs. So you've got the main tab, which is your main data analysis or data collection and analysis, and then you've also got the importance of repetition, which I'll talk about in a second. So the first page is where they will actually record all of their measurements, both simulation-wise and actual distance-wise. So just as a reminder, we're comparing how far a real robot will go given a certain programmed simulation distance and comparing what happens in the real world. So here's what they'll see. They will pick one of these quantities that they will change. So from the previous videos, you can change motor speed, you can change the runtime, or if for the advanced students, you can change the encoder count. So they will just select one of these and just delete all the others just to tell you which one they changed. And as they start to fill in the data, it will actually populate this chart for you. So the reason that I put 0, 0 is because you can't actually make a chart if there are no data points. It actually won't even let you. It'll kind of get angry at you. So I had put in a 0, 0 just so that I could actually make a chart, and then you can see that it pre-populates like this. You can also have a conversation with your students about the fact that if you do not program it to go anywhere, it will not go anywhere. So that is actually a valid measured point, which is convenient. It's a good starting point. So let's say that they're running through the activity and they program it to go 30 centimeters and it actually goes 28. Cool. There's your first real measurement. Then let's say you program it to go 50 and it goes, I don't know, 45. Then let's say 80 and it actually jumps up to like 86. Okay, and then you program 100 and it goes to 92, maybe 120, and it goes to 108 or just something like that. You can see that the chart reacts to everything that you are inputting. I think that that's really great because especially in other science classes where you kind of know that you have a certain trend that you should see, like in physics or chemistry, if there's a data point that goes in that is really, really not following the trend as it should be, that's a quick check for the students to see, did I like not zero my sensor, or was I looking at my ruler wrong or something? And they can kind of do some real-time error analysis like that. So that's why I like it so much. So that would be one like hypothetical set, but I would also want them to take multiple trials. So for example, they might do another at 30 that goes to, I don't know, 34. Okay, and then you can see right down here on the chart, there are 2 points at that 30 centimeter simulated distance, but it went to different distances in reality. So something that you might see. When they're all done and they do however many data points they can at however many trials, then they can take the longest actual distance traveled for each one, so the longest at 30, the longest at 50, the longest at 80, so on, and put it in this first data table right here, which will then have this chart populate. And then do the same thing, but for the shortest distance. So this tab is showing why taking multiple trials is important. And I can actually show you an example of that right now. So this is just the template and how to use it. But let's look at what an actual sample student piece might look like. So I have one set up here. And this might be an example of if they decided to change motor speed and keep everything else the same, something that looks like this. I tried to make this somewhat like reality. Obviously, theirs was probably not going to be as clean, but what they should see is the further your robot goes, the more error there is. And that's just inherent in mechanical systems. The longer that systems run, the more error there is. So what I tried to show is I took multiple trials of 3 at each of these points, although I would want my students to do like 5 or 7 or something. Like the more is always better. But just to show you what this would look like. So at earlier or shorter distances, there's not a lot of error. And then as it goes further on, there's there's more error. And you can see this looks kind of linear at first, but it's not really linear. So what I would want them to actually do with this is to figure out what is the function that actually fits this data. So what you can do here is you click on the chart, these little three dots in the upper right, go to Edit Chart, Customize Series, and you can add a trend line right here. So the trend line will automatically be set as linear. I want you to have them, well, you can choose if you want to discuss this or not. I'm going to discuss it because I think it's a really powerful statistical tool to use, even if they don't fully understand where it comes from. This R squared value is basically tells you how good of a fit the trend line actually is. So this linear relationship, if you look up at the formula right here, here's the formula for this line. It has an R squared of 0.943. That's pretty good. An R value of 1, or R squared value of 1 means that the fit is perfect. So the closer to 1 that you get, the better. It will never go past 1. You can't have more than perfect. And the lower, obviously, the closer to 0, 0 is a completely imperfect fit. So this is actually pretty good, but you can see that this is still not linear. We have a set before, at the very beginning, that lies below the line, and a set that primarily lies below the line at the very end, and then this portion in the middle lies above the line. So that tells you that there's a curve. So we can choose these different types, maybe polynomial. Polynomial fits this a little better. Notice 0.983. That's an even better R squared value, so that's a good contender. Switch to maybe logarithmic. 0.887, you can see this line really doesn't work, so it's not going to be that one. Maybe go to power series. 0.987, this is pretty good. And actually, if we compare that to a polynomial, that's actually a little better in terms of the R squared value. And this is where fully understanding where the R squared actually comes in, but you can have a conversation with them and still see, like, look at this. This fit is not as curved as what it should be. And so you can actually then say, well, really, this, not exponential, sorry, polynomial fit is the best contender for this set. Okay. Um, you also want to make sure that you use the equation in the label. So this label will actually say none originally, and you can say use equation, and then that's where the equation comes from. So right there, that's the polynomial that describes this. Then you need to click R squared again. Okay, so this would be the actual data set that they would gather, or an example of. And then what would they do to show this idea that multiple trials is really important? So click on the importance of repetition, and this first table is taking all of the longest actual distances traveled for each of the simulated distances. So they're going to have to go through and kind of filter and see, well, at 5 centimeters, the longest it traveled was 4.7. At 15, the longest was 14.4, so on. So take all those longest values, put them in here, do the exact same for the shortest values, put them in here, and you can see the two different charts. Again, they will pre-populate as it goes, and then you can have them do the formulas and the R squared values and everything. I just have it set up here already. So just looking at this, you can see, well, the shape is already a little different. This one is a little more curved than that one. And then you can actually compare the formulas. And you can go as detailed into this as you want, depending on the math skills of your students. What they're probably going to notice is, well, these formulas are actually really, really similar. And yes, that is true. Especially with shorter distances, you're not going to see a lot of error. But the main point that I want to make with them is, well, what if we used each of these formulas separately to predict how far the robot would travel at, say, like 300 centimeters? If you use those formulas, you're going to see that the error there is huge. There's going to be maybe like 20 or 30 centimeter differences. And if you're going for a challenge that is very, very reliant on being accurate, you need very precise results. So you need to know exactly how far you're trying to go. So 1 inch plus or minus 0.001 inch or something. That precision really matters. And then you need the estimated result to be as accurate as possible. Otherwise, for this challenge example, your robot might fall off the table or whatever it is that you're trying to do. So it really does matter, and that's why they shouldn't just do one trial of each and say, oh, I know exactly what the robot's going to do, because they don't. So once they see that and see the differences, then they can actually go back to the real data set, the full fit of everything that they've measured, use this to predict how far to actually go, and then they're done. All right, so that's how you use this activity template. Thanks.